Hello, good morning to all of you. So we have to consider here we are going to see the second section of your stereochemistry paper. The paper code is CHO-352. The first section is related to stereochemistry of carbon compounds, and the second section is related to asymmetric synthesis. Okay, so for the study of asymmetric synthesis, we should know the basic concepts about the stereochemistry. That is, what is meant by absolute configuration, that is R and S configuration. What is meant by relative configuration, that is D and L configuration. Then how the stereochemistry is changing while doing the chemical reactions. Okay, so what is the stability as per the energy requirement of the starting compound and the product and the intermediate or the transition state. So all these are the introductory part or the basic concepts of stereochemistry, and based on this a second section is introduced to you in your syllabus, and that is known as asymmetric synthesis. So dear friends, so this asymmetric synthesis is very interesting topic, just like your stereochemistry. So to gain the knowledge of this asymmetric synthesis, we should know the meaning of this title, asymmetric synthesis. So that's why in introduction we will see the title meaning, that is what is meant by asymmetric synthesis. So dear friends, when we are doing number of chemical reactions on paper or in the chemical laboratory, chemistry laboratory, then we come across different types of products formed in these chemical reactions. If our starting materials are achiral, means that are not chiral, and if there is a chance of formation of two enantiomeric products, that is a chance of formation of racemic mixture, then we are getting a pair of enantiomers, that is a racemic mixture, and that racemic mixture is giving in different proportions, that we called as a enantioselectivity. Okay, and this enantioselectivity is different for different chemical reactions, and hence EE, that is enantiomeric excess of every reaction, might be different. Now the main basic thing is, if our starting materials are achiral or our reagents are achiral, then definitely we are getting racemic mixture, that is a pair of enantiomers. These are enantiomers are nothing but non-superimposable mirror images of each other, and they are having same physical and chemical properties. They are only differ by their optical rotation. So optical activity is different only in case of enantiomers, and their all physical and chemical properties are same. So that's why such optical isomers or enantiomers are difficult to separate. They can be separated, but tedious job is there to separate the enantiomers. So such products, enantiomeric products or racemic mixtures, is not useful at all for the their use or their applications in different field, such as pharmaceuticals, then medicines, then as a pheromones, okay, etc. So to control the stereochemistry of the products, we should control the stereochemistry of the starting materials or the stereochemistry of the reagents that we call. And hence, due to this, we should think about the how to control the stereochemistry of product which are formed in the chemical reaction. And hence, there is a strong need to control the stereochemistry of the product, because if the product is giving, a particular reaction is giving two products, and one product is having R, that stereochemistry of that product is R, let us say, it is rotating the plane of PPL towards the right hand side, that is, it is dextrorotatory, so that is, we are denoting it by a plus sign. So if it is R isomer, and if this R isomer is active for a particular disease, or it is active medicine for to control the particular disease or to control particular parasite or virus in the organism. If this is the R form is active form, the S form which will be levorotatory, denoted by minus sign. So S isomer among that enantiomeric pair will be maybe inactive. Okay, so they are showing different activities. So that's why in this case, let us say this R isomer is useful, or it is showing a proper activity against the control, against the growth of some microorganisms or viruses which are growing in the other organisms or host body, and we are controlling, we are using that compound, that final product, for the control of that parasite or for the control of that disease. Okay, so it's let us say, we can say that this compound has a therapeutic use or pharmacological use. Okay, and if R isomer is active, in some cases the S isomer of that compound, of the same compound, may be inactive or it may be not useful. Okay, but if we are getting a racemic mixture of these two in our reaction mixture, then such products are not useful, because whatever the percentage of this S isomer which is formed in that particular reaction, this S isomer is inhibiting the activity of this R isomer. Okay, and ultimately there is no any such use of such type of products. Okay, so that's why we should control the stereochemistry of the product which is forming in the final forming in the chemical reaction by the controlling of stereochemistry of the starting materials, either by using chiral reagents or chiral starting compounds. And this is the meaning of asymmetric synthesis. So asymmetric synthesis is nothing but thinking or applying the strategy of how to control the stereochemistry of the product. How to control the stereochemistry of the product, that can be achieved by the meaning of, or by the means of, asymmetric synthesis. So we are synthesizing the product, we are synthesizing that particular molecule by controlling the stereochemistry of starting material or by the reagent. Ultimately it results into the controlled stereochemistry of the product. Okay, so that's why this technique or this strategy is known as asymmetric synthesis. Okay, I think you got it. During the course of time you will learn all these things. It's a very interesting topic, asymmetric synthesis. Okay, now the next topic is the chiral pool. Next topic is the chiral pool. So chiral pool. Chiral pool is the nature's ready-made chiral centers. nature's ready-made chiral centers. So as I have already told you that we have to think about such starting materials which are already chiral in nature. Means these chiral centers have their specific stereochemistry which ultimately results into their stereochemistry of the product. So such compounds are known as chiral starting materials. Okay, means they have asymmetric centers in their molecule, or we can say the chirality is there in as a whole. The molecule is a chiral in the structure of that compound. So what is this chiral pool? If we have to synthesize a molecule which have a fixed stereochemistry, let us say a molecule which has only a chiral center, which has only a single chiral centers in that in the structure of that molecule. Okay, and if we have to synthesize the R isomer of a particular compound, then apply such strategy such that our product must come with R absolute configuration. Okay, and to get this we should think about the starting materials or the reagents which are already having chiral centers, and in our nature there are number of such readily available, cheaper and easily obtained materials which are naturally occurring containing chiral centers in their structures. Okay, and such compounds are known as, or the collection of such compounds, collection, pool means collection of such natural, cheapest, easily available, that's why I am written here ready-made, easily available, and the most thing is enantiomerically pure, compounds is called as chiral pool. Pool means a bunch or a collection. Okay, so collection of such easily available molecules or the starting materials or the reagents which are naturally occurring, the cheaper source is there, and which are easily available, that is ready-made. We have a ready-made source of such materials, and the most thing is they are enantiomerically pure. So no other enantiomer of that compounds are present. Okay, so that's why they are enantiomerically pure. 100% enantiomerically pure compounds are there, and such collection of such compounds is known as chiral pool. Such collection or such group of such molecules is known as chiral pool. Okay, now the examples of chiral pool are nothing but all naturally occurring amino acids and sugars. So amino acids and sugars are the available in the nature. Sugars means that these are nothing but carbohydrates. Okay, and they all are having a fixed stereochemistry in their starting materials. So all of them are called as chiral pool. Okay, so these are enantiomerically pure. So that's why when we are starting our reaction with our such enantiomerically pure and naturally occurring starting materials, they results into the formation of enantiomerically pure which are giving a single enantiomer of the product, and there is no any formation of racemic mixture. So that's why we are getting an enantiomerically pure compound. Okay, so that's why there is no any chance of formation of unauthorized enantiomer of that reaction. Okay, so such strategy is called as asymmetric synthesis. Now there are number of examples of chiral pool. Okay, so first of all we will see the two main examples or two basic examples of the chiral pool, and these are amino acids. Amino acids, all naturally occurring L amino acids are having S configuration, So all naturally occurring L amino acids have their absolute configuration is S. Okay, so in this case the stereochemistry of the starting material, that is amino acid, is fixed, that is all are having S configuration. So ultimately the derivatives from which are found by the using of these amino acids must be having S configuration in their reactions or in their product. Okay, so that's why we can draw here a general structure of amino acids are COOH, RCH2, CORCH, here NH2 is beta, above the plane, and hydrogen is alpha below the plane. Okay, so this is a general structure of any amino acids. Okay, and let us find out the absolute configuration of this molecule. So nitrogen having atomic number 7, it will get priority 1. So second will be carbonyl group of acid COOH, third will be alkyl group, any alkyl group present in this, and fourth priority will be to the hydrogen atom. So how the molecule is moving? The priority is moving from 1, 2, 3. So it is moving anti-clockwise, and fourth priority group is at below the plane or away from the observer. So this priority retains as it is. So it is S configuration. So in this case, this is an only general example of amino acids. So all L amino acids are having S configuration. So this is the major source of amino acids as a chiral pool. They are used as a chiral starting centers. So this carbon is a chiral center or asymmetric carbon atom is there. So the stereochemistry is retained in the product formed by the this amino acid. Okay, so these are maybe anything, alkyl group, aryl group, or any side chain is there. Okay, so we know that there are 20 amino acids are found in nature and we can use all these 20 amino acids which are enantiomerically pure. All are they having S configuration in the synthesis of organic synthesis of different molecules. Okay, so that's why this is a use of chiral pool in the form of amino acids. Then the second example is carbohydrates or sugars. Sugars or carbohydrates. Sugars or carbohydrates or their derivatives. Okay, so we know that sugars or carbohydrates, glucose, mannose, erythrose, threones, all these are the examples of sugars. Okay, and the stereochemistry of all the carbon atoms in these molecules or sugars is also fixed, and that's why they can be used. They are also enantiomerically pure and easily available. Sugars are easily available in the nature, so they can be used as a chiral pool for the asymmetric synthesis. So this is a general concept of asymmetric synthesis and chiral pool. Okay, now we have to so example of this is, for example, D-mannose. Okay, D-mannose is the example. So what is the structure of D-mannose? The structure is very simple, and we are writing here the open chain formula CH2OH, CH2OH, CHOH, 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 again CHOH, and here CHO. So this is example D-mannose. And the stereochemistry, there are 1, 2, 3 and 4 chiral centers are there. So the stereochemistry is fixed here. Okay, and this is the ready-made available sugar in the nature. So that's why such type of sugar molecules or carbohydrate molecules can be used in our synthesis and for the asymmetric synthesis purpose, and hence the name asymmetric synthesis or chiral pool. This is the concept of chiral pool. Okay, so pool is there, or a collection of molecules is there, ready-made available, naturally occurring and enantiomerically pure. This word is very important, enantiomerically pure. So there is no any either 0.1% of another enantiomer is present in these molecules. Okay, so that's why such compounds are treated as chiral pool. Okay, now we can see some examples, then you can understand the concept in detail, or your concept will be very clear. Okay, chiral pool. Let us see the preparation of aspartame. Preparation of aspartame. Okay, now I am writing here the retrosynthesis of aspartame molecule. So the structure of aspartame is PHCH2 CO2Me. So this ester is there, NH CO NH2 CH2 CO2H. Okay, so only one, there are 2 chiral centers actually, this one and this one. Both are having S configuration. Yes. Okay, so this is the structure of aspartame molecule. So when we do a retrosynthesis, okay, of this aspartame molecule, then you might be seen here amide bond, NHCO. This amide bond is there. So by doing cleavage at the amide bond, you may get the two molecules PHCH2 CO2Me. Okay, and this will be NH2. This will be NH2. The stereochemistry is here. Yes, again. Okay, so we get this molecule after breaking the amide bond, and the second molecule will be CO. So this will give you COOH. Okay, as this is amide bond, so this amide bond may be found between this amino group of this molecule and this carboxylic acid functional group of this molecule. So COOH will be there, and here NH2 group alpha, then CO2H. Okay, sorry, CH2 CO2H. Okay, so this is the chiral centers. So what is this molecule? This is S-phenylalanine. This molecule is a methyl ester of S-phenylalanine. S-phenylalanine. S-phenylalanine is the naturally occurring amino acids. This is S-phenylalanine. This is the structure, and this molecule is aspartic acid. aspartic acid. Yes, aspartic acid. So it's a dicarboxylic acid and the name is aspartic acid. Why yes? Because the stereochemistry of this chiral center is yes. The stereochemistry of this chiral center is yes. So it's a yes phenylalanine. Yes phenylalanine is a naturally occurring amino acid and it's a methyl ester. Okay. So stereochemistry is retained and the stereochemistry of this carbon is also retained in the naturally occurring aspartic acid. Okay. So that's why we can synthesize this aspartame molecule. We can synthesize this aspartame molecule, which is artificial sweetener generally used in many food products. Okay, and this can be synthesized by the amide coupling between this phenylalanine and this aspartic acid. So it's a very easy concept how to control the stereochemistry of these two chiral centers by the synthesis of naturally occurring amide coupling reaction between S-phenylalanine and S-aspartic acid. So that's why the stereochemistry of the product is retained because of the stereochemistry of the starting material is fixed, that is yes, and they are naturally occurring. So that's why they are enantiomerically pure. There is no any chance of R-phenylalanine or R-aspartic acid. Okay, so that's why this product is obtained as a pure. Then the next example is synthesis of S minus epsinol. Synthesis of S minus epsinol. IPSENOL. Epsinol is there, so epsinol, so the word is having OL at the suffix, so it must be alcohol. So yes, what is the significance of this yes? Yes is its stereochemistry of the molecule. Minus sign indicates that this molecule is levorotatory, or it is rotating the plane of PPL towards the left hand side. Okay, so that's why it is denoted by minus sign. So we have to synthesize this yes epsinol. Okay, so our strategy is, the structure of epsinol is like this: CH2OH. So hydroxy is beta, then CH2, diene is there. So this diene is there. Okay, and this hydroxy group is present above the plane. Okay, and this is the chiral center. Now find out the absolute configuration. First priority, then second priority, third priority, 1 2 3. Fourth priority group is below the plane, so 1 2 3 anti-clockwise. So this is S epsinol is there. So when we do a retrosynthesis of this molecule, then we can get here this compound can be obtained from the easily available S-leucine, and the structure of S-leucine is NH2 CO2H. Okay, so this is not obtained directly. We have done here retrosynthetic analysis on this molecule. Our target is how to obtain this stereochemistry. Yes, here at this chiral center, how to obtain this stereochemistry with the same side chain. So side chain is isobutyl group 1 2 3 4. Isobutyl group is there, and isobutyl group is as it is here. Okay, so that's why the stereochemistry of this product is retained, because we can use here the naturally occurring enantiomerically pure this amino acid, and this name of this amino acid is S-leucine, S minus Leucine. Okay, so if you know the structures of all 20 amino acids with their correct side chains and the structures of sugars, then you can easily point out the molecules required for the asymmetric synthesis. Okay. So this is a retrosynthetic analysis. Then in the synthesis process, this NH2 amino group can be converted into hydroxy group. Okay, in the synthesis process. Now the actual synthesis of this epsinol can be done by using this S-leucine. So CH2 NH2 COOH. Okay, so this is a primary amine group. We can convert here. We have to convert this amino group into hydroxy group. So what is the reaction? The best example is diazotization reaction. So convert this an amino group into hydroxy group by diazotization reaction, that is HNO2 then water. Okay, hydrolysis. So what will happen? CS2, we are getting hydroxyl. NH2 group will be converted to okay, we will write the N2 plus. Okay, N2 plus, the intermediate formed by the reaction of this amino acid with this nitrous acid HNO2, and here it is COOH. COOH. So I have written this carboxylic acid functional group in detail structure. Okay. Now in this case, this NH2 group is beta, that is above the plane. That's why this N2 group is also beta. Now the lone pair on the hydroxy group, oxygen atom, will attacking on this carbon atom. Okay, and N2 group will be knockout, because nitrogen, diatomic nitrogen, is the best living group, and that's why this is a SN2 attack. Okay, so it's a backside attack of this hydroxy group, of this lone pair of oxygen present on the hydroxy group. Okay, and hence we can see this, as this hydroxy group is present within the same molecule, we can treat as a SNI reaction, that is neighboring group participation, NGP, of this hydroxy. Okay, actually it is SN2 attack. Okay, and we can say that this reaction is SNI because it's neighboring group participation, NGP. Okay, and what we get here? We get an intermediate, and the structure of intermediate will be like this, minus N2. N2 will be knockout here, and the structure will be an 3-membered ring with oxygen, CO, this carbon 1, 2, 3. Okay, so first carbon, second carbon, and third atom is oxygen atom is 1, 2, 3, and there is a carbonyl. Okay, so as N2 is beta, hydrogen is alpha here. So hydrogen remain alpha here, hydrogen remain alpha. Okay, and that's why now this intermediate OS2 will be opened by attack of water molecule. Okay, and hence the product will be isobutyl group, then hydroxy. Okay, COOH, hydrogen. Okay, so in this way we have converted the S-leucine starting material, which is obtained in the nature in a numerically pure compound, into this compound, okay, which is a one of the part of this S epsilon. Okay, so that's why this is a strategy that we have applied here. Now another strategy. So this is the one of the part of this molecule. Now how to introduce this part? Okay, this COOH, this carbon is this carbon, this carbon carboxylic acid carbon is now attached to the this part. Okay, so that's why we have to synthesize this molecule in this way. First of all, protect that hydroxy group. So we have isobutylene group, beta hydroxy group is there, CO2H. Okay, then use protection. I think you have a knowledge of protection, deprotection. So this is THP protection, tetrahydropyran protection, H plus. This is THP protection of hydroxy group. Then you will get OTHP, and CO2H group is as it is. Okay, so the stereochemistry is still written here. Then convert this carboxylic acid into ester by reaction with alcohol. Then you will get OTHP, CO2H. Okay, and then COOR. So acid functionality is converted to ester functionality here. Then reduction, lithium aluminum hydride, LH. What will happen? OTHP as it is, CH2OH. Ester is converted to primary alcohol by using lithium aluminum hydride. Okay, now again do a protection of this hydroxy group by using tosyl chloride and pyridine. Tosyl chloride and pyridine. So this hydroxy group is converted into tosylate group. Okay, so you will get OTHP, CS2, OTS. Why there is a need to convert this hydroxy into tosylate? Because hydroxy group is not a good living group. We are converting it into a best living group, that is a tosylate group. Now, okay, so still the stereochemistry is written here. Okay, there is no any change. Now what we have to do here? Pyridine is used as a base to neutralize this HCl formed in the reaction. Now this OTHP is get deprotection of this tetrahydropyran protection of this hydroxy. This hydroxy is protected here in the form of THP protection. So deprotect this group. After deprotection you will get free hydroxy group here. So deprotection is done by acid. Okay, so by using acid this hydroxy group will be generated, and by using base what will happen? There is acidic proton on hydroxy, so base will abstract that acidic proton, O minus will be generated, and this O minus will attack on this carbon atom. Okay, tosylate group will be knockout, so OTS will be knockout. O minus will attack on this carbon atom. There is a formation of epoxide ring, 3-membered epoxide, and there is a knock of leaving group of this tosylate group will be leaved out. Okay, and you will get here this isobutyl group. Okay, the stereochemistry is not changing here because O minus is attacking. There is no any breaking of this carbon oxygen bond, so the stereochemistry is retained here. Okay, so O minus is attacking on this carbon, so 1 2 3 membered ring epoxide ring formation will be there, and OTS minus will be knockout. So this molecule we are getting. Now use Grignard addition reaction on this epoxide. So the Grignard will be, so we are making so this part will be the Grignard reagent, a diene. Now how to prepare this diene, that is not the part of our discussion. Okay, so magnesium bromide. So when this Grignard reagent we have, this Grignard reagent will attack on this carbon atom. Okay, and hence there is a breaking of this carbon oxygen single bond, and this CH2 group will now have this part of the Grignard reagent, and we have our final molecule, that is isobutyl group, hydroxy CH2 and this. Okay, so this part of this Grignard reagent coming, or it is incorporated into the molecule, and this part is from the S-leucine part. 1 2 3 4 5 1 2 3 4 5 6 carbon, 1 2 3 4 5 6 carbon. These 6 carbon are from the S-leucine molecule, and this 1 2 3 4 are from the Grignard reagent. Okay, so this is the synthesis of S-ipsinol molecule. Now when you study this molecule properly, you can easily understand what is the meaning of actually chiral pool or asymmetric synthesis. So in this example you will able to find out the stereochemistry of this final product, that is S-ipsinol, is fixed and it is S configuration. Now we have to synthesize this molecule, so that's why we have to do the asymmetric synthesis, retrosynthesis here, and by applying knowledge of retrosynthesis we are getting a simple molecule, that is S-leucine, which is a naturally available and easily available optically pure compound, S-leucine. So that's why we have started our synthesis from the S-leucine, and by doing a number of reactions finally we are getting here the target molecule S-leucine. Okay, this is very interesting actually, but you have to study at all, you have to study properly, then and then you will get all these things. And the next example is synthesis of R-sulcatol. Synthesis of R-sulcatol. So all these examples and reactions are important from your exam point of view. Okay, so I am drawing here the structures of R-sulcatol and S-sulcatol. OH, CH2, CH2. Okay, so this is R-sulcatol, and this is the structure of S-sulcatol. Again the suffix is OL, that's why it is alcohol. Okay, and this is the structure of this alcohol. Aliphatic chain is there with a carbon-carbon double bond at one of the end of the molecule. Okay, so we have to synthesize R-sulcatol here. So what is this R-sulcatol? R-sulcatol is a natural pheromone. R-sulcatol is a natural pheromone. So what are pheromones? Pheromones are the compounds which are used to attract the male insects by using a smell or a pheromone, okay, which is secreted by the female insects, okay, and they can be trapped by using traps in the crops, okay. So this is one of the technology for the pest control, and for this use of this pheromone in the pest control, the R-salketal is used. So R-salketal is a natural occurring pheromone, and the R-salketal and S-salketal are present in 65 as to 35% mixture in the that pheromone, okay. So that's why our target is to synthesize this R-salketal and S-salketal separately. Enantiomerically pure R-salketal and S-salketal we have to prepare, and we have to mix them properly in a proper ratio as to 65 to 35, okay. So that's why it's a challenge to us how to synthesize these two molecules separately. There is only change, the stereochemistry of this chiral center is different. This is R and this is S. So we have to, first of all, we have to do a synthesis of R-salketal. See here. So this R-salketal can be prepared by a simple starting material which is known as 2-deoxy-D-ribose. 2-deoxy-D-ribose, and this is our target molecule, and the starting material is 2-deoxy-D-ribose. The furanose structure is there, 5-membered furanose structure is there. This hydroxy group may be alpha or beta, no problem, but the stereochemistry of all other carbon atoms is fixed. This is alpha and this is beta, CH2OH, CH2OH, beta, okay, 2-deoxy-D-ribose. Now we can open this molecule and we can get CH2OH, CHOH, OH, CH2,